Hi, my name is Maddie Sandin and I'm a mathematics major at the University of Kentucky. The purpose of this video will be to introduce the concept of stereology, which involves looking at 2D images to determine the 3D shape of an object. Thousands of years ago, the Chinese people used a unique form of storytelling called shadow puppetry as a form of entertainment. Cut-out shapes were put in front of a light source, projecting images onto a screen. Musicians and singers use their talents to share the story the puppets are portraying. For an example of one of these stories might have looked like, check out this website. You may have also participated in a similar form of shadow puppetry. Have you ever made a dog or rabbit shadow with your hands? Your fingers and hands act as the puppet, while the light source projects your hand's creation on the wall. You can see more examples of this at the following website. As you can see, light and shadows have long been used to make art and tell stories. However, the contrast created between light and shadow can also be important in understanding concepts in science. Stereology involves interpreting 2D images from cross-sections of a 3D object to determine its 3D shape. For example, when we view this box from above, we can see a triangle within the box. However, if we adjust our viewing angle, looking at the side of the box, we can only see a single line. Imagine this box is clear, and we shine a light on the side of the box. A single line would project onto the wall. If we divided the box into sections, we would see different lengths of lines. Now imagine this same box has a sphere inside it. If we shine a light through it, a circle will project on the wall, and if we divide the box into sections, different sized circles will project onto the screen. These images show stereology in practice. We can use the 2D images that project on the wall to form an idea of what the entire object looks like before it was cut into various sections. Practically speaking, scientists can use these methods to solve real-world problems. Consider the synapses between nerves. Vesicles fuse at synapses, releasing neurotransmitters. Researchers need to determine the diameter of vesicles, but only when a small slice can be put under a microscope. It's not possible to be sure the exact diameter of a vesicle. By looking at several slices of the synapse and graphing the diameters of the circles, one can estimate the diameter and volume of the vesicles. Now we can walk through a simple example. On this first worksheet, following example A, we can see that the specimen was cut into 3 1-centimeter sections, and when we project these slices onto a wall, we get that the lengths of the specimen are 1, 3, and 4 centimeters. So it's going to look something like this, is a rough sketch of what we have. We have 1 centimeter, 3 centimeters, and 4 centimeters. And now this is going to look like several rectangles stacked into a pyramid, each section of the pyramid being 1 centimeter thick, like this. And so we can calculate the total area of this pyramid by taking the area of each individual rectangle, which would be 1 times 1, 1 times 3, and 1 times 4. And when we add all of these values up, we're going to get that the total area of this triangle is 8 centimeters squared. While this gives us a very rough estimate of the total area of the specimen, we could get a better approximation. Remember that the projected image is showing the longest part of the specimen on the wall, but the specimen is not actually 3 different rectangles. We can correct for this by turning the 3 steps into 5. For the smallest section, which is this one, we won't change anything because we have no other slice to average it with. For the second section, which we originally had as 3 centimeters long, we will draw a line through the middle, creating 2 half-centimeter sections. So now these each become half a centimeter. The length of the top section will become 2 centimeters. And we determine this by taking the difference of the two sections, so 3 centimeters minus 1 centimeter, which equals 2 centimeters. And then we have 1/4 of 2, which is going to give us 1/2. So we're going to take 1/2 of a centimeter off of the top section. And that's going to create this length right here as 2 centimeters. Then we will repeat the same process on the bottom section. So we're going to get 2 half-centimeter sections, like so. We'll take the difference, which will be 4 centimeters minus 3 centimeters, which is 1. 1/4 of 1 is 0.25, so then we will take 0.25 off of each end of that 4 centimeter section to get a 3.5 centimeter section. So now we're going to take our new area, which is going to be 1 times 1, which equals 1 centimeter squared. The next section is going to be 3 centimeters by 0.5 centimeters to give us 1.5 centimeters squared. This section will be 3.5 centimeters by 0.5 centimeters to give us 1.75 centimeters squared. And then this section will be 4 centimeters by 0.5 centimeters to give us 2 centimeters squared. And when we add all of this up, we're going to get 7.25 centimeters squared. And as you can see with this new figure that we've made by doing these averages, by shading the sections that we've cut out, we're going to get still a stair step, but it's just more accurate to what our actual specimen would look like. Even then, we could find a better approximation for total area. Consider that each of the end slices probably wouldn't reach the edge of the slice. To take the averages of the sections, we use a half because as you watch this triangle move across the 3 sections, you can see that it could be anywhere along these sections, but half would be the average, so that's what we use in our calculations. We will cut the length of the 2 sections in half. Therefore, this 1 centimeter section that we have here, we're going to cut it in half to 0.5 centimeters, essentially taking this out because it's not going to reach the edge. The longer section down here with the 3.5 centimeter and 4 centimeter sections will also become 0.5 centimeters thick, but we don't want to lose the correction we did in part 2, so we will reduce the lengths of each section to 0.25 centimeters, creating an end specimen that is still just 0.5 centimeters thick. So how we're going to do this is divide this in half. This is going to give us 2 sections here that are 0.25 centimeters, like this. This will be completely taken out, and our new sections will be this 3.5 centimeter section right here, and then a 4 centimeter section right here. So our stair step now is a little bit smaller. We've taken half a centimeter off each end to create a more accurate measurement. So now if we take the areas of each section, we can get a better area. So we're going to take 1 centimeter times 0.5 centimeters, which is going to give you 0.5 centimeters squared. Then we're going to take 2 centimeters times 0.5 centimeters to get 1 centimeter squared. We will take 3 times 0.5 to give you 1.5 centimeters squared. Now we're going to take this 3.5 centimeter section times 0.25, and then we'll take this section, this 4 centimeter section, times 0.25 as well. Okay, So the 3.5 times 0.25 is going to give you 0.875 centimeters squared, and 4 times 0.25 is 1 centimeter squared. And when we add these up, we're going to get that the total area of our triangle is 4.875 centimeters squared. Now if we look at our stair-step image now, we can see that it is smaller with smaller steps, and it's going to be more accurate to what our actual specimen might look like. Now assume we are told the actual specimen is a triangle. We can find the true area of our specimen. Recall that to determine the area of a triangle, we take 1/2 the base times the height. Based on what was projected on the wall, we know that the base is 4 centimeters. So we have an actual triangle, and the base is going to be 4 centimeters. For the height, remember that the ends of the specimen only reach halfway to the end pieces. Our height is then the total 3 centimeters, which is what we originally had, minus 1/2 that we took off from the top, plus the 1/2 we took off from the bottom, which is going to be 3 minus 1, which equals 2. So the height of our triangle is 2 centimeters. If we do the formula for the area of a triangle, we're going to get 1/2 the base times the height, which is going to give us 4 centimeters squared. So if we look, the actual area of our specimen is 4 centimeters squared, and we actually started out with 8 centimeters squared. So our closest approximation was the 4.875 centimeters squared, which we got when we had done all of the measurements and the averaging. So now you can see that it really is very important to be able to look at the specimen and correct it for possible errors in the area. So as you can see from this general exercise, we can see how much error occurs if one does not consider various assumptions in the potential errors in measurements. If you are considering subtle changes in the structure due to experimental manipulations, then we can readily see how much of a change is needed to be larger than the potential area in the measurements. The 2D versus 3D view of a form can be challenging to understand, but learning to think that way develops a scientific problem-solving skill. The 2D versus 3D view of a form can be challenging to understand, but learning to think that way develops a scientific problem-solving skill. When we look at a DNA molecule, like this 3D example, from the end, looking in, we can only see a circular shape. Most people probably wouldn't be able to identify this as a DNA molecule based solely on this image. However, when we change the orientation of our view, like this, it becomes obvious that this is in fact a DNA molecule, as the double helix structure is now apparent. However, in some cases, the only way to determine the actual 3D structure of DNA might be with 2D slices that look like this image. In cases like this, the analysis we just worked through becomes very important for piecing together a complete picture of our specimen.